Today is another day, and today we'll be discussing another part of the electrical double layer. Remember that in our previous class we have discussed the um, the Helmholtz model of the electrical double layer, and today we are going to be looking at the Gouy-Chapman model. So we're going to look at the Gouy-Chapman, the Gouy-Chapman model, the Gouy-Chapman model. Okay. So today we are going to look at the Gouy-Chapman model of the electrical double layer. Remember that we had mentioned that the electrical double layer generally find applications in so many areas, especially in colloid chemistry, where you discuss things like formation, production of drugs, production of paints, inks, creams, soaps, and many other things. And then you can also find its application in electrochemistry, where you talk about dissolution of what, of electrodes in solution. Now we also say that it finds application in biochemistry, when you are talking about enzymes formation and also a couple of colloidal materials in solution. Today we are going to look at the Gouy-Chapman, but let me first refresh our memory that we had said that the Helmholtz model is the very beginning of discussion of the electrical double layer. It is the most simplest aspect of the electrical double layer. It was found around 1850 by Helmholtz, okay, von Helmholtz, and he believes in his theory that once you have a metal immersed in a solution or in an electrolyte, electrolyte solution, you have that metal dissolve. Why it is dissolving? It is because the metal is undergoing oxidation, and when it undergo oxidation, it dissolves, and that dissolution will allow for what, a loss of all the positive ions from the metal into the solution or the electrolyte, and concentrate that electrolyte, leaving a concentration of negative charges, housed on or housed by the electrode. And in that way it is going to now give rise for the migration of what, of the negative, of positive charges that are concentrated in the electrolyte due to their higher density, to do what, to move by just an electrostatic force, or by electrostatic interaction, to what, to the to the surface of the metal, balancing the charges. And that balancing of charges will allow for two layers. One is the outer Helmholtz plane, and the other one is the surface charges plane of the metal, and those two give rise to what we call a parallel plate. And that, of course, is what we call the electrical double layer. And that double layer is the reason why you do not have milk, that milk in a tin turning from its fat nature into butter. There's no coagulation. The same thing in drugs that you have, same thing in creams and all those kind of things. Now, what makes the Helmholtz layer very different is because he believed that the ions or charges that are concentrated in this particular electrode are rigid. So because of that rigidity, there is no mixing or diffusion of ions or of molecules. That is the reason why, that deficiency is the reason why the Gouy-Chapman model came. Now, the Gouy-Chapman model, what is different in the Gouy-Chapman model compared to what, to the Helmholtz model? It is simple. It is because of the introduction of the diffuse layer. The Gouy-Chapman model believes that there is a diffuse layer in the electrical double layer. That wherever there is an electrolyte and an emission of an electrode, there is also a diffuse layer that is a little bit distant away from the electrical double layer, or rather from the outer Helmholtz plane, which is quite closer to what, to the electrode. Now, that is the major thing that makes the Gouy-Chapman model very different from that of the Helmholtz. And that particular reason is why we are now able to explain certain biochemical reactions under biochemistry. which were not possible in their discussion in the Helmholtz model. Now let us put down something that will guide us in the understanding of the Gouy-Chapman model. Now the Gouy-Chapman model looks like this. Let us assume that this is what we have here is our electrode that is built with positive charges. Our electrode built with positive charges. Okay, so our electrode is built with positive charges here. Okay, now let us now look at the fact that at this point here we have the interface. All right, we have the interface at this point here. We have the interface at this point here, and then we have negative charges. Okay, we have negative charges aligning themselves at this point. Okay, we have negative charges aligning themselves at this point. Okay, and then we also have negative charges around this area. Okay, closer to this area. We have all these are negative charges, and then all these are negative charges. Okay, positive charge around here. Let's say we have another positive charge around here. We have negative. Then we have this layer here, and here we have negative charges with a concentration of positive charges also here. Okay. Okay. So you can see that from this diagram here, we have this is our electrode. This is our electrode. Okay. And these are the surface charges. These are the surface charges, which are point charges. Okay, these are the surface charges on the metal, positive charges on the metal. And then this, of course, let's write them in this way. Okay, we'll have the positive signs. Let's write them in this way so we could understand something. Okay. Okay, so these, of course, are our solvated cations. Okay, solvated cations. Why these, of course, are defined. Okay, let me not take from there. Let me take from here. This, of course, is our anions. This is the diffused. This is the diffused layer. Okay, this is the diffused layer. This line here is the diffused layer. Let me write it here. This is the diffused plane, or you call it the diffused layer. Okay. Now, with this diagram, we can be able to explain what Gouy-Chapman is talking about the electrical double layer. But of course, we should know that from here to here is also defined as the diffused layer. Okay, this is the diffused plane, and this is the diffuse layer. Now, this, of course, can also be described as the Gouy-Chapman layer. Now, at this point in time, we need to understand that here is what you define as your double layer. Okay, this is the electrical double layer at this point here. This point here defines the layer. That is that interface. That interface between the metal and the electrolyte. The whole of this is electrolyte. The whole of this is electrolyte. Okay, and this is the metal immersed there. What Gouy-Chapman is saying is simple. That this particular surface charges on this particular electrode, that this particular surface charges are simply defined as point charges. That they are point charges, and because they are point charges, they have a higher electron density. Let's look at the electrode potential. Now, if we define here as our electrode potential for the initial, this is how it goes. So it means that if this is your electrode potential and this defines your um, the electrode point, it means that at the electrode where we have point charges, okay, it means that we have a balanced surface. According to Gouy-Chapman, the electrode is having a balanced surface where the charges, which are point charges, are spread uniformly on the electrode surface. And if they are spread uniformly on the electrode surface, then it means that the electrode potential is high. Therefore, you have a higher what? Electron density. The excess electron density is high at this particular electrode where point charges are spread, where electrons or charges are points and are spread uniformly. So if you have higher excess charges, then there is a possibility that these particular point charges will definitely diffuse into this particular electrolyte. That is what Gouy-Chapman is saying. Unlike Helmholtz, Helmholtz says these particular charges you have here are rigid, and that they are rigid, and even the outer Helmholtz plane is rigid. In that way, you cannot have any of these charges diffuse into the solution. So that is why how do you call him? That is why Helmholtz had a problem, because Helmholtz believed that there was no diffusion or mixing of the charges in this particular surface with the solution. There is no proper interaction. Electrostatic ions are the ones that allow for the movement of these particular ions that are here. But Gouy-Chapman is saying no. Number one, that there is a possibility for diffusion because the surface of this particular electrode going into the electrolyte is plane, and as it is flat and plane, there is a uniform distribution of the charges on this particular electrode on the basis of the fact that they are point charges, and the fact that we have a higher excess charge density on this particular electrode, it can possibly allow for diffusion of the excess ions into the solution. Yes. And then he also believed that, look, it is not enough to feel that the charges that you have in this particular electrolyte cannot move. They can only move by electrostatic forces. No, he said it's not true. That if you look at the entire electrolyte, there is a point where you have concentrations of electrons. Then there is also in the electrolyte a particular point you can define as your diffuse layer, where these electrons of the counterion, for example, you can call them, which are the negative charges, will be attracted and they move gradually to this point. And they can move away from the bulk of, this is the bulk of the electrolyte. They filter themselves through a plane where you have a diffuse plane, and you have more of the negative charges of the counterion that are now closer to what? To the outer Helmholtz plane, where they can balance the charges on the electrode. Now he says that in this particular plane where you have the electrolyte, there is always what you call thermal forces, and that around this particular plane where you have electrode, there is always what he called electric forces. Now, what he means here is this: that this particular charges, okay, or you call the counterion, or you could call them electrons that you have concentrated in the electrolyte, will always possess a thermal force or thermal motion, and because of that thermal motion, they are forced to do what? Undergo agitation with the solution. And if they undergo agitation with the solution, there is a possibility that they can possibly be affected by the thermal agitation, and then they will have to do what? Have to start moving by that heat presence. So he do not really believe that these particular charges or these particular electrons are moving because of electrostatic forces. So he said that there are thermal forces in the water, in the electrolyte, and there are electric forces here. The electric forces have a higher charge density, okay, than the thermal forces. So since they have higher charge density, there is a tendency that through electric forces, these charges that we have here can do what? Can diffuse into the solution. In as much as you also have these particular electrons undergoing thermal forces can also have a way of migrating to what? To balance the charges at this place, allowing the electrical double layer to remain balanced. Now, what are we saying in essence? What we are saying is simple. The major drawback of the Helmholtz was because Helmholtz believed that the electrical double layer at the outer Helmholtz plane is rigid. There is no diffusion or mixing of charges of the electrode with that of the solution. But the Gouy-Chapman is saying no. There exists what? A diffuse layer. So he introduced the diffuse layer, and as he introduced the diffuse layer, his explanation is simple, that there is a possibility of diffusion of these particular charges on this particular electrode to the solution of the electrolyte, because according to him the charges are point charges. 1. 2. Because the surface is flat and the electrons are all spread uniformly on the surface. 3. Because the excess charge density on the electrode is higher than the one on the solution, there is a possibility for diffusion of electrons from here to this point. 4. Because the electrode possesses electric forces and then the solution possesses thermal forces, there is always agitation by thermal forces on these particular electrodes, which are the counterions, by the charges of the solution, thereby allowing those counterions to diffuse away from their counterpart, which are the solvated cations, into the diffuse layer, where they can now come up to do what? To form not really to form, but to do what? To equate or to balance the charges that have probably lost by the process of a lot of factors. Now, if we take a look back to what we have discussed earlier concerning the milk, for example, or let's go away from the milk. Let us look at the formation of electrolysis. Okay, so if this was an electrode, you sip it in, you put it into an electrolyte. What Gouy-Chapman is saying is there will be a loss of what? Charges into the solution at the first instance, and this charge that will lost in the solution, it is because of what? Because of oxidation. Now, when the charges lost in the solution, the opposite charges will remain. Those charges that will remain, okay, will need to draw another opposite charge from the solution to balance the process of electrolysis. At the point where there is a loss of charges from this particular electrode into the solution, that electrolytical cell is going to become imbalanced. For it to remain in its balanced state, like equilibrium, there must be a continuous diffusion of the counterions gradually to the outer Helmholtz plane to make up for the ones that has been lost. In that way, there exists an equilibrium or a balance between the counterions ions and the surface ions or charges, thereby maintaining what? The electrical double layer for the electrolysis process to continue normally. That is exactly what happened even in your creams. Otherwise, your creams will just one day you wake up and see your creams all blocked. They are not good again. Or otherwise, one day you wake up one day and you find your vegetable oil or your palm oil blocked. It's not working again. Or the same thing, you find your milk in the container blocked into what? Into butter, and it's no more your milk. The same thing with your creams, same thing with your soap, the same thing with your drugs. So, the work of the Gouy-Chapman was very crucial. It was because of the work of Gouy-Chapman that the biochemists were now able to explain what happened around the interface of enzymes. What happened around the interface of certain reactions, biochemical reactions that exist. You can see that the presence of the diffuse layer, which is the major contribution of Gouy-Chapman to the electrical double layer as opposed that of Helmholtz, play a significant role in both chemistry and biochemistry. I am glad that we have this class. I'm sure you've learned something about the Gouy-Chapman model of the electrochemical double layer. Do not forget to make your colleagues part of it by doing what? Sharing. Share this class. Please, 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 that's what you owe me. Share this class. Share it to your friends, share it to your colleagues, share it to your groups. Tell them to subscribe, to follow us, to enjoy this class and other classes. Don't forget to like, to leave comments. Don't forget also to go to my Facebook page, and then you see type Dr. B chemistry classes or Dr. B science classes. You are going to get me. Do not forget to follow. Don't forget to also share those pages with your friends. Don't forget to leave comments, to like, and to follow. Until next time, it's been a beautiful moment. Enjoy yourself.